when you connect them, you see a traversing of electrons. And as soon as the battery, or like for example the connection is being given, so the difference in the potential energy is termed as electromotive force. Okay, and it is generally measured in terms of volts. Okay, so this we have already discussed. And how do we measure this is with respect to standard hydrogen electrode. So that is given as 0. With respect to that, we have either higher or lower. Okay. Again, when you have a positive electrode potential, it means it's a spontaneous kind of reaction. And very important point in that is the electrode potential of a half cell reaction is also temperature dependent. Okay, this is very simple logic. If you heat, you have a lot of electrons which are traversing and so on. Okay, so here you can see the electrochemical series, like for example electrochemical series, where you can see hydrogen is termed as 0 electrode potential, and other things are all positive potentials, and remaining all are negative. So what it means, positive standard electrode potential means they are very good oxidizing agents, and more negative means they are good reducing agents. Okay, so even this topic we had already discussed. Now, even we have done an calculation where if they ask you to figure out what is the electrode potential of a cell, that is given by cathode minus anode. Okay, so for example, this is the reaction we asked you to find out, and by looking at the values, we can get the electrode potential of a cell as 1.1 electron volt. Okay, such kind of questions you can get for your 1 mark, where they give you the values and they ask you to find out. But only thing is, you should remember the cell potential of the cell you can get from cathode potential minus anode potential. And this terminology also we had discussed in our last class, where we connect Gibbs free energy and Faraday and electrode potential. Okay, this is the expression. Okay, and you are already aware that delta G is minus RT natural logarithm K. Okay, now if you relate both, okay, minus NFE and RT ln K, you can write E naught as RT by NF ln K. Okay, so if you equate these two, so these are some expressions with which you can bring in the electrode potential into the Gibbs free energy expression. And the term K means equilibrium constant. For example, how much reactants are being converted into products. All those points we already covered. Now, one more from here, I think everyone would like to observe carefully, is we have looked at reaction constant or equilibrium constant. Now, what is reaction coefficient? So in reaction coefficient, which means you can use general Nernst equation, and if you want to use for galvanic cell and all, for a general reaction, any reaction means reactants and you're getting products, and these are number of moles. Okay, concentration, this is A, B, small a, all those. If you want to define reaction coefficient, means products concentrations. Okay, products, what are the concentrations, divided by reactants concentrations. Okay, so how you get reaction coefficient is by substituting reactant and product concentrations or partial pressures if it is in gaseous forms at any point during a equilibrium kind of situation. This is a very important terminology. Till now, you are looking at only the products concentration. Like for example, with respect to products concentration, that is the reason we call them reaction equilibrium or equilibrium constant. But now you also call it as reaction coefficient, where products concentration is divided by reactant concentration. This is also termed as Q. Now, why are we learning this? You might be wondering. First of all, we are looking at spontaneity of a reaction, and then we went to uh, its free energy, like for example delta G, and then we introduced like electrochemistry. Why are we learning all this? If you look at it, okay, the answer is very simple. We want to look at Nernst equation. Okay, so can someone tell me what is the Nernst equation from a very general, in a general way, or whatever expression you remember from the Nernst equation? Anyone in the class? Like, how is the expression for the Nernst equation? Yeah, go ahead, go ahead.
Sir, E naught minus 0.529
Hmm.
log.
0, yes, E naught minus 0.0529. Okay. But after that, there is one more important term.
Sir, log of.
Hmm. Okay. So,
cathode
somewhere
by anode.
cathode by anode. Okay. Let's see. We'll see that. Okay. Now most of you are coming close to that. Now, just think, why are we talking about electrode, for example, electrode potential, or for example, why we are talking about reaction coefficient? So generally, Nernst equation under standard conditions, this is you can derive Nernst equation using this expression. Okay, you know that E naught of a cell is reduction minus oxidation or cathode minus anode, and delta G under standard conditions is minus NFE naught. Okay, now just apply this in this expression, then you get. Okay, now based on thermodynamics and also by looking at non-standard conditions related to Gibbs free energy and using Gibbs free energy at standard condition means delta G naught means E naught, because these two are Faraday's constant and N is number of electrons transferred. So if E naught means delta G naught, like that we can use. So you also know this is the expression. Delta G is equal to delta G naught plus RT ln Q. Q is reaction coefficient. Reaction coefficient means product's concentration divided by reactant's concentration. Okay. If you all of you, if you have a piece of paper or a notes or like that, please take this a simple derivation. This derivation you can get for um, like 4 or 6 marks with a combination. Like for example, derive Nernst equation and apply it for some potentiometry titration like that. Okay, so all of you take down a step by step. You from here, delta G is equal to delta G naught from thermodynamics. This is the first expression we have taken. Then what we do is, you are all aware that delta G naught is MFE. Okay, it means work done and how much of voltage you apply here. Okay, so then you substitute delta G is minus NFE and delta G naught is NFE naught. Just start substituting this. Okay, and then tell me like what will be the expression. What will be
Minus NFE plus RT ln Q.
minus NFE. So see, wherever G is there, NFE. G naught is there, NFE naught, because other things are all constant. Okay, and you
So
know the value of.
G naught equal to NFE plus RT ln
Yes,
ln Q.
yes, like it is like natural logarithm you want to take. So this is the expression all of you get first. Now here, what you do, you can divide by minus NF. If you divide this expression, also please take down all of you. if you divide this by NF, so what you can do is E is equal to E naught, because minus minus gets cancelled, and RT by NF with a minus sign because it is plus here, natural logarithm of reaction coefficient. So reaction coefficient is product's concentration divided by reactant's concentration. Okay, so this is the next expression. Yeah. So I hope all of you have taken down these 4 expressions. Okay, now you know the value of R, you know at what temperature it is going to be a number of electrons transferred, and Faraday also you are aware of Faraday constant. Okay, so this expression turns out to be very simple, and you know what is the concentration of products versus reactants. Okay, then you also know that we can rearrange this expression by this term, like uh, these are for a reaction A and B reactants giving to C and B products. This is the expression. Reaction coefficient is products divided by reactant concentration. Okay, so what we have done from here to here is you just included reaction coefficient as products concentration divided by reactants concentration. That's all. And this, either this form or this terminology is referred as Nernst equation. Okay, so this you can get for 4 marks or an 8-mark question combining Nernst equation along with an application of Nernst equation. Okay, so it is a very very important question you can expect for your essay type, even for your assignments and so on, and lot of your experiments in are based on Nernst equation, electrochemistry based experiments. Okay, so what is the use of Nernst equation is we can calculate the cell potential of any galvanic cell at any concentration. Whatever may be the concentration, you can calculate the cell potential of the particular equation, yeah, of a particular system. Okay. So is there any like doubt on this, so that now we can expand the terms and we can go more deeper with respect to that? Any clarification needed? Any doubt with respect to the derivation or like that?
No.
So let's look at it. Now we know the value of R. We know what is the Faraday things. Then you apply and rearrange this expression. If you use this, we get E under standard electropotential conditions, E naught minus 0.0591 2 volts. Okay, after all these expressions, and by number of electrons transferred times reaction coefficient. Okay, so what we can use this expression is to find out cell under non-standard, means you know the cell under standard conditions how much it behaves, like for example at 273 Kelvin or like that. But if you want to look at other temperatures or other concentrations, then you use this expression. And, or you can determine the reactant or product concentration. You know this. You can also determine the concentration of reactants or products. Okay, so even for example, like you have copper 5 molar and zinc in a Daniell cell 0.05 molar. If they ask you to calculate for this expression, we can easily calculate the electrode potential of the cell as 1.1 volt. We can recap what we have discussed in that standard cell with the different electrode potentials, along with knowing the concentrations. Okay, if you know the concentrations also, by using this expression, we can calculate the electrode potential of the cell. Okay, now, so if I want to give you an idea about what exactly the Nernst equation will talk is. Nernst equation will tell you why the EMF of a voltaic cell drops when cell discharges. For example, why it discharges means you have lot of reactants are being converted into products, and at the equilibrium, okay, as soon as the reaction, like for example, if by the for example cell is like discharging some power or like that, at that time the product concentration decreases. Okay, when the product concentration decreases, which is in the like numerator, automatically the expression, overall expression will be decreased. Okay, so that is the reason why it discharges, because you can see here, okay, as this part reduces, overall factor also will be reduced, and as the reactants are converted into products, the for example, the uh, reaction coefficient increases, and then the value of E decreases. And what happens at equilibrium means when the uh, reactants and products are of same concentration, we get like natural logarithm 1, where it becomes 0. Okay, so you already know that uh, if it is Z is equal to 0, when E is equal to also 0, so there is no free energy in that system. And also remember, when the system is at equilibrium means equal number of products versus equal number of reactants are together, then what happens? G is equal to 0. Okay, and so which means when E is equal to 0, you have seen the cell reaction has the reaction has stopped, or there is no reaction which is going on. Okay, this is just by looking at the Nernst equation. Okay, other than this basic techniques, we can also look at the important applications of Nernst equation in potentiometer titration, which we have carried out day before yesterday. Okay, all of you must have looked at potential change. For example, what happens when Fe2 plus is changing to Fe3 plus? How much is the voltage change? Okay, that we have seen like for probably in millivolts, and what is the concentration you can find out. Okay, you know the electrode potential, from that you can calculate the concentration, or even acid based titrations, or acid based reactions, or you can go for various like redox kind of titrations. Okay, so again this is to recap for all of you what is potentiometer titration. Again, one important point I would like to inform is during an essay type question in Nernst equation, you can expect derived Nernst equation followed by potentiometer titration discussion. Okay, can come for complete 8 marks or even sometimes 12 marks, where you want to really elaborate potentiometer titration, theory behind it, and write applications. Okay, so and one good thing with this experiment is you have already done this experiment in lab, so you can, it is very easy to make a appropriate points out of it. Okay, so potentiometer titration, you are already aware it's an electrochemical method. Okay, where there is a change in potential with respect to the change of ions, and yeah, when you can see that if you have ions with electrons which are being out, it can be like you can like reduce or oxidize accordingly. Yeah. So because of this change in ionic species, like ionic, for example, different ions are there, we see the cell potential varies. Okay, the best example being copper 0 to copper 2, or Fe2 plus to Fe0, where the small electrode changes will be affected in the EMF. Okay, now, so what in um, we are going to look at the potentiometer titration is, we have an reference electrode indicator electrode. So indicator electrode is the where we are looking at the ion concentration. Okay, where this is the it is indicating your what is the concentration, and you have the reference electron where it is calomel electrode. Okay, or it can be hydrogen electrode also, or standard hydrogen. And this indicator electrode will tell you after forming an electrochemical half cell, and this will tell you what is the concentration or what is the ionic flow. For example, Fe2 plus Fe3 plus, how much is being transferred and all, you can get an idea. Okay, now if what is the overall potential from potentiometer titration is the electrode potential of the overall cell potential is indicator minus reference and the what is the existing solution in that. Okay, for example, from the indicator electrode. So in this case, are the unknown kind of solutions, we see a sudden potential drop or change between the two electrodes. And then what we do, we measure from that the electrochemical cell of the complete reaction. And you have already seen how much volume you add versus how much is the change in electrode potential. The jump, you can easily calculate the volume followed by the concentration. Okay. So this, I think I do not want to elaborate more, but um, this is the thing by which we can do all these potentiometry based iterations. Okay. And then by looking at the Nernst equation, you can write E is equal to E naught and RTNF by the concentration, whatever you are looking for, means Fe2 plus to the Fe3 plus. Okay, you know this potential, and then you have various factors, and then you can calculate the either the concentration or E for a particular reaction. Very, very important is the potential of a given sample is proportional to what are the electroactive ions. Means, for example, here Fe2 plus in the titration what we have done recently. So we are looking at how much of Fe2 plus ions are being oxidized into Fe3. So essentially Fe2 plus. So the electroactive concentrations only we are looking. Now, again, I don't want to go into the details, like because since it is already there in your manual and also you must have noted from your experimental section. First, whichever you are going to titrate, take in a beaker, and then you find out the EMF. Then you add the titrant until you see some change in EMF, and there is a sudden change in EMF. That point you should be careful. So this is what the first part of your experiment. Okay, so at one point you suddenly see a increase and then it saturates. But you're adding in high amounts here, 1 ml, 2 ml, like that you'll be adding. In order to get the accurate endpoint, what you do from this region to this region, you do a slow, even you can do even from point 0 also. But you know that this is the change where we are going to see the huge from here and here. So at this place, you get a very nice huge shift. Okay, so this part also I think many of you are already aware of. And we can also perform like acid based iterations, where instead of we can use reference electrode as like a caramel electrode, and glass electrode also we can use. And instead of adding indicators, we can add at one particular place like equivalence point. Okay, and that if you do from this range to here, you can easily get the sharp endpoint for an acid based titration. And How do you know what is the cell potential is this concentration by logarithm of hydrogen ion concentration. Okay, see, one point, if you use like ln, it is like natural logarithm. If you use log to base 10, multiply by 2.303. I think that part, I think many of you are already aware of. Okay? So that is the reason, if you simplify this expression, we get E naught minus 0.01, how much of log concentration. Okay? So this is all about uh, various potentiometer titrations or acid-base titrations applied from Nernst equation. Okay. Okay, and also you can do like oxidation reduction kind of reaction. For example, you can see here Fe2 plus is converted into Fe3 plus. Okay, so here also, how do you calculate Nernst equation is oxidized versus reduced species. Okay, so these are the different applications of Nernst equation. So the main reason in which I'm like rushing, or why I'm giving you the important outputs of this, is since you have already done this experiments, for example in acid-base titration, what you're going to do next also, all of them they employ Nernst equation, and you can also see this expression as like the immediate outcome of Nernst equation and more accurate results as compared to a normal titrations. If you do a normal titration, you need indicator. So here you don't want indicator. Very small concentrations you can do it. Okay? So these are the important points which I would like to like highlight, and with respect to, for example, various kinds of titrations followed by the application of Nernst equation. Now, is there any doubt till here on this particular topic, so that we can? I will just discuss one or two points about corrosion. Later we will, um, or after the exam doubts, we can go to corrosion topic also. Is there any doubts or like that on this Nernst equation and its applications? I'll also give you the handout today on this particular topics, and you can have a look into that, along with your practical material, where we talk and based more on this Nernst equation and so on. Yeah, any clarification?
No, sir.
Okay. Okay, so let's, yeah, Amitoj, go ahead.
Sir, can you please share a model question paper for tomorrow's chemistry exam?
Yeah, we'll discuss. So shall we discuss first that, or last 5 minutes, or like that we can discuss? Okay. Um, okay, so what we will do now, 10:35 your class will get over, no? Okay. Okay, now what we'll do is, I don't want to discuss more today about this. We can just begin our. As I told Amitoj, I will talk about this your all the multiple choice questions or kind of pattern, like very shortly. Like just give me in last 5 minutes or 10 minutes we can discuss. Now, can someone tell me what is the, for example, what exactly you understand by corrosion? What do you mean by like corrosion?
Oxidation.
Oxidation. Any other point? Any other, or
So
like,
the point at which the metals,
hmm. Go ahead,
so the
Anurag.
point at which, so the point at which the metals stop giving hydrogen, stop replacing hydrogen, like
Stop
Fe3O4.
hydrogen, or what is that? Stop giving hydrogen. Okay. Yeah,
So,
I
like in
here.
iron, when the upper layer of iron get oxidized by water, it absorbs water vapor. There is a
Hmm.
redox take place, and due to which the electrons becomes free and they attract more oxygen from the
Yes. Okay.
atmosphere.
Okay. So as all the three of you pointed out, basically we are looking at iron oxidation or hydrogen evolution depending from the water or all those, depending on how it makes a cell, which is the environment, if it is in basic environment or acidic environment or neutral environment. Okay, so that is corrosion. And any other metal do you think can corrode, or any other material can corrode?
Sir, aluminium.
AG.
Ag,
Copper.
aluminum, copper. Okay, yeah, I hear quite a lot.
Zinc also, sir.
Gold.
Zinc. Okay. Gold. Yeah. So, Shilam, I think gold is not that. Silver is a good example, but gold is not still. It can like that is the reason why it is used in jewelry, because it has no corrosion. Like for example, least corrosion aspects. Okay, that is one point. And one more important aspect which we would like to also discuss is what it has to do with electrode potential. What corrosion has to do with electrode potential? Like for example, you mentioned, some of you told the oxidation, reduction, all those process. You have like same thing we can consider as an electrode, which gets oxidized. Okay, it get reduced. And what is the thing which makes up basic corrosions? Okay, so that is also very important aspect. And with respect to thermodynamics, what way corrosion needs to be understood. Okay, and very you have a very important kind of question for an essay type question and all, which is on four-way diagram. Okay, so we have almost three classes or two classes to cover four-way diagram. We'll slowly do it like from tomorrow and so on, these topics. Okay, now um, like what we can do today very quickly is I will first give you few aspects regarding corrosion. Mm, 35, yeah, it's only 10:20 now. Let me uh, first I shall give you, for example, what is corrosion or what exactly are we going to discuss. Just I will give you like a, okay, so just let us look at what is corrosion with respect to free energy. Okay, free energy of a corrosion reaction. Till now, you know, you are telling oxidation. It's and for example, if a material gets corroded, what are the changes in the property of that particular material? Anyone in the class? Like for example, what are the important properties of the corroded materials? Whether it is same as that of initial one, or it gets some problems or like that. Anyone? Or you can also define what are the problems of like corrosion. Anyone would like to point out? Okay. Or last question in any way. What do you think are the ways to control corrosion? How can we control corrosion?
Galvanization, sir.
Galvanization. Yeah. Any other thing? So in galvanization, like how exactly you're going to like modify the corrosion, or for example, treat the corrosion?
Sir, electrode plating on the metal.
Electroplating on the metal. Okay, so that is one such uh, way of treating the corrosion. Any other treatment of to prevent corrosion?
Adding impurity.
Adding impurity. Okay, that seems very general, but let's see. Yeah. Any other point? Okay, we will see like what exactly is corrosion, and in just see if someone asks you what is corrosion means, you can straight away say it is an attack of environment on materials. Now, what you all of you told is with respect to iron, but you can have metal oxidation or how polymers also get degraded with reaction with oxygen, or how these ceramic refractories they get dissolved in molten materials, or irradiation based damage. So these all are termed as corrosion. Okay, corrosion doesn't mean with respect to only iron getting oxidized. We have several other points as well. Now, for your syllabus point of view and all, let us go more into metal oxidation. Okay. Now, why you must be thinking why I should learn corrosion? Okay, like why? Because already I know that iron gets oxidized and I can galvanize and over. That's it. But why it is very important to learn corrosion? I ask especially engineers is because you see it's day-to-day activities. For example, if you tease like a nail kept in normal water, saline water, and acidic kind of water, and you can also have marine-based corrosion. Like for example, you see wood being corroded under constant water, or the dams or roofs which are placed, they get corroded. Okay, so this was a question which I was asking you. What happens when a material gets corroded? Means its load transfer capacity reduces a lot. Okay, means the dams or whatever or that tracks, railway based tracks or like that, they have a very good load transfer resistance. But once they get corroded, they become weak, so it cannot do the best. So because of all this, you should understand and to prevent corrosion. So this is what, as I told you, we will try to discuss. And like there are several ways in with respect to like metal-based corrosions, like construction materials or ships, or where you have harsh chemical environments, where it also gets corroded because you have water and you have like metallic system where it can get corroded. I will probably stop at this stage and let us discuss more with after the class, after the exam, more about. Um, okay, now